All right, kids, this is a little addendum. You can see I'm wearing a slightly different shirt than last time. It turns out that my initial math for the repeated measures t-test was incorrect. Little sad face. Thank you to Agia, by the way, for pointing it out and demarcating exactly the issues. So here's what it is. Before, I had miscalculated S. So here we have the same numbers, and so this little add-in is just replacing the part where I had a little math error. Remember, this is a study where we were looking at whether a particular diet reduced weight. So this is 3 different people. This is their weights at time 1. This is their weights at time 2. And you remember we went all the way through d minus d bar squared, and we got sigma d minus d bar squared. So the sum of the squared deviation scores between each difference and each mean difference is 266.67. Okay, now remember T equals d bar over S sub m. So we're going to use all this information to figure out S sub m. So we're moving toward that. S squared is our best estimate of sigma squared, which is our best estimate of the population level variance, equals sigma d minus d bar squared divided by n minus 1, which is 266.67 divided by 2. Okay, so that's S squared, which is 133.34. We will need that to figure out S sub m, but here's a little sidebar, and it was the sidebar that I had gotten wrong before. So here's the sidebar up here. You remember that when you're computing T, you don't use S, but S is critical. S is our best estimate of the population level standard deviation, and it will be used in computing Cohen's d, or the effect size, which I'm simply going to do right now. Usually I'll do it later, but just because I kind of messed up and this is a little inserted sidebar. So S equals the square root of S squared. And S squared is 133.34. The square root of that, you get that with your little calculator, is 11.55. That's the thing I messed up before. So Cohen's d, as typical, is going to be d bar, so the size of your mean differences, divided by S. You remember, Cohen's d is always something that has an estimate of the population level standard deviation in the denominator, in the bottom of it. So Cohen's d, it's absolute value, it's 33.33, that's d bar, divided by S, which is 11.59, it equals 2.89. And that is your correct Cohen's d. That is the main correction from what I had messed up before, but we're all good, kids. You're now watching the corrected chapter 10. Okay, so that's Cohen's d, and of course that's a very big effect size. If an effect size of 0.8 is defined as large, then this is like ginormous, might be the scientific term for that. So let's go back to our t. T equals d bar divided by S sub m. Divided by S sub m. S square sub m equals S square divided by n, which is 133.34 divided by 3. We're going to put that at 44.45, and thereby S sub m is the square root of S square sub m, which is 6.67. Thereby making T equals d bar 33.33 divided by 6.67. So it's 33.33 divided by 6.67. That's going to come to 4.997. Let me just do that one more time. Just to make sure. Yeah, so that rounds to 5.0. So t equals 5.0. And you remember the way that we do this, now that we have t, or what I sometimes call t obtained, we're going to compare t obtained with t critical. So now I'm going to erase all this, but it's on video, so if you need it, you can hit that rewind button. Okay, so here is our t distribution. Remember, t distribution has a mean of 0. And our t critical, which we computed in the prior step, is 2.92. Okay, that was based on this being a one-tailed test, and that was based on an alpha of 0.05. So this region here is 5% or 0.05 of the distribution. And to be able to reject the null hypothesis, we're going to need t to be more extreme than t critical, and it is. Okay, so t obtained equals 5.0, which is more extreme than t critical. So our final step in the hypothesis testing procedure, step number 5, we're going to comment on the null hypothesis, and we're going to reject the null hypothesis. So we're going to reject the null hypothesis. You remember the research hypothesis, H sub 1, was that d bar cap, or a predicted d bar, those numbers were predicted to be greater than 0, because the second column was predicted to be smaller numbers than the first column, so the differences were predicted to be positive numbers. The null hypothesis was that d bar cap is less than or equal to 0, and we have just rejected that, supporting the idea that that predicted pattern, that the differences were positive in nature, meaning that there was weight loss, that the weights at time 2 were lower than the weights at time 1, were on average positive and likely represent a positive difference at the population level for this particular nutritional treatment. There you go, kids. Chapter 10, Stats with Glenn.